Okay, we're going to do some section 1.5 review problems. For our first problem, we're going to solve this double inequality, negative 3 less than 2x plus 1 over 3 less than 3. And it's a double linear inequality. We have a linear expression in the middle. And the way we solve this is to do operations on all three parts and get x all by itself in the middle. So the first thing you'd want to do is multiply all three parts by 3, then solve for x from there. So see if you can do that. So when you do multiply all three parts by 3, the 3 in the middle, the denominator in the middle cancels. You get negative 9 less than 2x plus 1 less than 9. Then we subtract 1 from all three parts, and that gives you negative 10 less than 2x less than 8. And then finally divide all three parts by 2. So our final result is negative 5 less than x less than positive 4. So now when we graph this, you may have learned using the open circles because we're not including the endpoint, but in this section we also covered the use of interval notation. We use the rounded brackets in place of the open circles, and we shade, and then the interval notation follows the graph. The left endpoint is 5 with the round bracket, comma, and then the right endpoint is 4 with the round bracket. So there's the answer in interval notation. Okay, our next problem is an absolute value inequality. Absolute value 2x plus 1 less than 4. Now for this type of inequality with absolute value, we learned that this 2x plus 1 is going to be sandwiched in between negative 4 and positive 4. So we can just rewrite this absolute value inequality as this double inequality. It's because this quantity inside the absolute value bars, if it's between negative 4 and positive 4, when we do the absolute value, it will be less than 4 because it'll be positive. So now we solve another double inequality. Subtract 1 from all three parts. So we have negative 5 less than 2x less than 3. And now divide all three parts by 2. And we get the answer negative 5 halves less than x less than 3 halves. And the interval notation would be negative 5 halves, comma, 3 halves with the rounded brackets. Now our next problem is an absolute value inequality using greater than. Now that's a bit different than the less than. What that means is 3x plus 1 greater than or equal to 5 gives us an answer. Because if we can find x so it's bigger than or equal to 5, when we triple it and add 1, we have a solution. But also, if 3x plus 1 is less than or equal to negative 5, we're also going to get another solution. So 3x plus 1 less than or equal to negative 5. So if we found an x value that when we tripled it and added 1, it was negative 6. When we absolute value that, it's positive 6, so it's bigger than 5, or equal to 5. So it's a different procedure for this type of inequality. So now we solve these two. So we subtract 1 from both sides in both of these inequalities, which gives us 3x greater than or equal to 4, or 3x less than or equal to negative 6. And then for both of these, we divide both sides by 3, x greater than or equal to 4/3, or x less than or equal to negative 6/3, which is x less than or equal to negative 2. Now, if we want to write the interval notation for this, we have two intervals. So the two intervals here, one goes from 4/3 up to infinity, and we include the 4/3, so we use the square bracket. The other interval is from negative infinity up to -2, because x is less than or equal to -2. Again, we use the square bracket. Now, the symbol for or, this interval or this or interval, is the big U, which means union of. So when you have two intervals like this, either or, you use a U in between them for the notation. Okay, our next problem is a polynomial inequality. This is not solved like a linear inequality. We can't go adding 4x squared to both sides and divide both sides by x squared. You get the wrong answer. What you have to do here is factor it and find the solutions to the related equation. Those are called the critical values. So when we let the left side equal 0, that's the related equation, we factor x squared out, x squared times x minus 4, then let each factor equal 0. We get x equals 0 or x equal 4. Those are the critical values. We plot these on the number line, and since it's greater than or equal to, we use closed circles. And we use closed circles here as I plotted them because 0 and 4 are themselves solutions. Both 0 and 4 give you 0 greater than or equal to 0. So 0 does equal 0. Those are solutions. So once we plot these, we have to figure out which regions of this number line, which intervals, make up the solution. To the left of 0, from 0 to 4, or to the right of 4. So to do that, we put in test values for each of those intervals. Now I'm going to start with the region or interval 1, to the left of 0. Pick any value to the left of 0. I'm going to pick -2. And you plug it into the factored form of the inequality, which would be x squared times x minus 4 greater than or equal to 0. That's what we're going to plug it into. Now when we plug it into that factored form, we get -2 squared times -2 minus 4. Well, that's +4 times -6. Now, positive times negative is not greater than or equal to 0. It's less than or equal to 0. So that's false. So we do not shade that region to the left of 0. Every value to the left of 0 is going to make the x squared factor positive because it's squared. And the x minus 4 is going to be negative. Anything minus 4 if it's to the left of 0, so you're going to get positive, negative. It's at these critical values that we get sign changes in the factors. So we go to the next test value. And for this next value, test value, I'm just going to pick 2 right in the middle of the interval. Plug it into the factored form of the inequality. 2 squared times 2 minus 4. Is that greater than or equal to 0? No, that's false. The first factor stayed positive, but the second factor is still negative. So we do not shade that second interval. So then we go to the third interval, and I'm going to pick let x equal 6. When we plug that in, we get 6 squared times 6 minus 4. Is that greater than or equal to 0? Well, that's 36 times 2. That's true. So we do shade the third interval. Now this is kind of an odd solution because we got this lone point 0 and also x greater than or equal to 4. And that's what our answer is. X equals 0 or x is greater than or equal to 4. And we have to include the x equals 0 because 0 gives you 0 cubed minus 4 times 0, which is 0, which is greater than or equal to 0. Okay, our next inequality is a rational inequality. It's a ratio of two algebraic expressions. We will solve this like the polynomial inequality we just did, except here to find the critical values, you let the numerator equal 0 and you let the denominator equal 0. And whatever those solutions are, those are your critical values. So we have 3x minus 9 equals 0, x plus 2 equals 0. So 3x equals 9, x equals 3, and x equals negative 2. Those are your two critical values. So you plot those critical values on the number line, and then we start testing regions, just like we did in the previous problem. Now, when students plot these critical values, they'll often plot them just like this. Closed circle at 3 because it's less than or equal to 0. And when x is 3, you get 9 minus 9. 0 over 5 is 0, which is less than or equal to 0. But what about negative 2? Negative 2 gives us negative 6 minus 9, negative 15 over 0. Well, that's division by 0. Okay, so here, the negative 2 critical value, we have to change that to an open circle because we cannot have division by 0. Negative 2 cannot be part of the solution. So I've changed that endpoint to an open circle. So that splits up our number line into 3 possible intervals for this inequality. To the left of negative 2, in between negative 2 and 3, and to the right of 3. So we start testing the intervals, just like we did in the previous problem. So if we let x equal negative 3, we plug it into the factored form of the inequality, where we factor the 3 out in the numerator. So that gives us 3 times negative 3 minus 3 over negative 3 plus 2. So we have 3 times a negative over a negative. So we have a negative numerator, a negative denominator, the whole fraction's positive. So that's not less than 0 or equal to 0, it's false. So the first interval does not work. Second interval, I would say let x equal 0. When we plug 0 into the inequality, the factored form, we have 3 times 0 minus 3, which is a negative 9, over 0 plus 2, a positive 2. Negative divided by positive is less than or equal to 0. So that second interval is part of the solution. Then for the third interval, let x equal 4. And when we let x equal 4, we get 3 times 4 minus 3 over 4 plus 2. We get a positive over a positive. You see how the signs are, how the factors change signs as we go from one interval to the next. And then in the first interval, we had a negative and a negative. The second interval, we had a negative, but then the second factor was positive. And then when we crossed from 3 into the third interval, we had a positive factor and a positive factor. So in the third interval, that's false because we have positive divided by positive. So here our only interval is the second. So that gives us the answer negative 2 less than x less than or equal to 3. And that'll be it for this video. We'll see you in discussions or class if you're in class.